Hi everybody, this is Christina and I'm here with Mark Arlett and he's the Vice President of Engineering for iFLY. Mark, would you just introduce yourself briefly, tell us a little bit about yourself and what you do with the company?
Yeah, I started with SkyVenture in 2000, not with SkyVenture, but doing SkyVenture work in 2002. SkyVenture, now known as iFLY, and as a consultant, and we did work for about 4 years. And then I joined the company in 2006 direct, and have been the VP of Engineering since that time. And we have a great team of people that we've assembled, mostly outside engineers, for the first 7 years or so that I was direct, and then the last 2 or 3 we've begun to hire some people internally, and so we have a great team both internally and externally. We maintain that external team as well. We've got a huge experience base there. And we do everything from early concept design to final detail design.
Okay.
And work with the fabricators and through the whole process. And then of course we have a large other, the rest of the team, production projects, and everybody else that support us on the design side.
Okay, cool. Later on in our interview, I'm going to ask you about what you're working on, like right now, like the latest and greatest stuff.
Okay.
But I want to back up and talk about like early days of iFLY, what you know, because I know you weren't there right at the beginning.
Right.
But how the company started, how the idea started, and early stages of engineering.
Okay. Well, the person that came up with the idea was a guy named Bill Kitchen. And he's no longer associated with the company. The current CEO purchased the company from him back in around 2002 or so, maybe 2001, somewhere right in that range. And he did his first skydive in 1990, and he's a thrill ride entrepreneur.
Okay.
And he thought, hey, we could make a machine that simulates skydiving. And so that's how the idea was born. And the first tunnel was built was designed and then built in Orlando back in 1997. It opened in 1998. And
the one that's still there.
The one that's still there.
One.
The very first one is still there, and it's as profitable as it's ever been. And it's doing very good. There's a lot of business there. And so then like I mentioned, in about 2002, Alan Metney ended up buying the company, but first, before that, he was a former world champion skydiver, and or was currently at that time a world champion skydiver with Airspeed team, and he was the biggest customer of the Orlando tunnel, teaching others how to do what he does, and he's the guy that had the vision, for what this could be. In the early days, before that, I've heard him say years ago that. They would sit around and go, well, how many wind tunnels could the world handle? And they were talking numbers like, is it 3, 4, 10? And we have 37 today, running with many more, in the works. So anyway, so he ended up purchasing the company in, I think, 2002, and had the dream, the vision, and it was around that time was when our paths crossed, and I became part of SkyVenture at the time.
Okay, so when we bring kids or when we bring anybody into the tunnel, and we ask them, how do you think this works? How do we create the airflow in here? Most people think it's fans, and almost everybody thinks the fans are right underneath,
down,
right?
Yes, they do.
Yeah, so why not? Like that seems like the easy solution, right?
Right. That's what, and the reason is air quality, airflow, and that's really in the original design. In the one that's in Orlando that I talked about, and this was part of Bill Kitchen and his engineering team that he put together to design that. They went for high quality airflow, and what that meant was putting the fans downstream of the test section, or the flight chamber, as we call it today. And so in that original tunnel, it was a single pass tunnel where the air enters the bottom and goes out, exits the top, goes through the flight chamber and then exits the top, and the fans are actually on top and they're pulling the air through.
Okay.
The problem with the original design, although as good as it is and was at the time, is that it's a lot less efficient, because you're having to accelerate that air from zero airspeed up to max and then back down to zero in a very short distance. And that's not a very efficient way ultimately to do it. But for a first design, it was fantastic.
Okay. So when you say like the quality of airflow, you mean if the fan was right under you, that the air coming off of the blades would just be so turbulent?
Yes, yes,
right?
yes,
Okay.
much more turbulent. There are wind tunnels around. There's one in Las Vegas.
People
like
talk about that.
Yeah.
They come in and say, "Oh, I've seen your tunnel in Las
No,
Vegas,"
it's
but
not
that's
us.
not ours.
us.
Yeah.
Definitely not us. Yeah.
Yeah.
Yeah, and I've been there once too. Unfortunately, I didn't fly at the time, but it's very turbulent airflow. And what we try to do is position the fans, even in our newer tunnels, as far upstream as possible from the flight chamber, so we have a chance to recondition that air.
Okay, to just get it all straightened out.
Right, to make it,
laminar.
Yes.
Okay, when it comes out.
100%.
Okay, super cool. And so you were talking about the getting the air moving from zero velocity, and that's not efficient. So is that what started the closed loop design?
Yes.
So,
Yeah. The recirculators, more or less.
Okay.
Yeah.
Because some of our people are working at the older tunnels where they don't have a closed loop design.
Right,
And then
right.
some people are going to be working at the brand spanking new ones.
Right,
So like
right.
what are the differences there, and how did that come about?
Yeah, it's really more than just flow quality. It's also comfort.
Okay.
Right. So like in Orlando, even though Orlando's in Florida, it still can be 40 degrees in the wintertime, maybe even in the high 30s. And you can imagine the wind chill factor at 40 degrees and 120 miles per hour. It's not very comfortable to fly at those conditions. And so fortunately there it doesn't happen very often. So it kind of limits you to where you could put a wind tunnel. You can't really put an open wind tunnel. You could, but it wouldn't be very comfortable like in Canada or or in the northern U.S. or places like that. And so in a recirculating tunnel, we can control the temperature. And we have multiple ways that we've done that over the years, which we'll talk about, I guess, in a minute. But so that's one thing. Flow quality is the other thing, because we can expand the loop. The loop is larger, and we can do a lot more with the air before we send it through the flight chamber. And then the big one is efficiency.
Okay.
Because we're taking advantage of that recirculating momentum of the air.
Because once it's moving, the fans just have to kind of keep it going.
Yeah, keep it going, yeah. There's a lot of drag, but still.
All right.
Way better than an open tunnel.
Okay. You mentioned the temperature. Do you want to talk about that, about controlling the
cooling.
temperature?
Yeah, what we did, obviously in the open tunnel you can't. You're subject to whatever the ambient temperatures are. The first thing we did in the first recirculator design, and that was when I became involved. I had nothing to do personally with any of the open tunnels. My first experience was the first recirculating tunnel.
Okay.
So all the recirculating tunnels we've done, my team has had involvement with that.
And where was that one, the first recirculator?
First recirculator was built in the UK.
Oh,
it's at
okay.
Milton Keynes in the United Kingdom. And the second one built was in Denver, Colorado.
Okay.
So those are basically the same design, just
Okay.
built two different locations. So what we did in the recirculator to control the temperature is we did some air exchange in the return air tower. So in the recirculator, the air goes up in the middle, obviously goes through some turning vanes, goes through the fans, goes through more turning vanes, and then in the return air tires, or what we affectionately call the rats.
Okay.
We have these gigantic doors. We call them louvers, or really dampers.
Okay.
And they're like 10 feet wide, 10 feet tall and about 25 feet wide. And one of them opens into the airflow facing into it, and the air goes down and it pulls the air out of the tunnel.
Okay.
And then there's one just slightly lower, a couple of feet lower on the opposite side of the return air tire that opens also into the airflow, but it hinges at the top.
Okay.
And so what it does is when the air goes through here, it's speeding up, causing the pressure to drop Bernoulli, right?
Right.
And then so therefore it sucks in more air. So we're pulling air out, and then just exchanging the air. And we exchange about 15% of the air when it's fully open.
Okay.
And that's enough to keep the tunnel cool at whatever temperature. And so depending on what the temperature is outside, if it's 40 degrees, you might have it open 20% of the way, and if it's 60 degrees outside, you might have it open even further, maybe 75% of the way, to keep it at the temperature that you want to keep the tunnel at. Now the problem with that is you have two issues with that. It works great for temperature control until you get above the temperature. If the external ambient is 90 degrees F or 100 degrees F, then you can't be any cooler than what it is outside.
Right.
So we found from flying, just my own personal experience, once it gets about 85, you start wondering, man, it's starting to get warm in here.
Oh yeah, Drew,
Yeah.
he was at Hollywood for so many years, and he talks about that he would just be dripping sweat because it's so warm.
Yeah, yeah.
Okay.
So that's one of the early louvered tunnels. That's the second design actually. That's in Hollywood. But so anyway, so you end up with this issue in the hot temperature zones, like in Austin where we are. It's great in the wintertime, not so good in the summertime. Still sufficient, but less comfortable for the patron. The other issue with a louvered tunnel is that whenever you're opening these big louvers into the airstream, you're creating turbulence.
Okay.
And that turbulence can be felt all the way around in the flight chamber. Now it's not really, it's not what do we call bad, but it's there. It's you can tell it's there, and it's not as good as our newer tunnels. So the next generation of cooling that we did, we decided, and this is really attributed to Alan Metney and his foresight as well. In each of the turns, we have turning vanes. They're basically curved airfoils, similar to an airplane wing. And that's really responsible for our, yes, there you go. That's really responsible for, it's a low drag turn. You really, technically you wouldn't have to do anything in the corner. You could just blow, just have a duct, you could make it curved or square or whatever, and the air would follow it around, but it would be very inefficient. You'd have a lot of friction in the air there, and you'd be very inefficient. You'd lose, it cost you a lot in energy. You'd need bigger fans, use a lot more electricity to force the air around the loop. So the turning vanes we have are low drag turns, and they're really key to keeping the efficiency. One of the things we do to keep the efficiency of the tunnel where we need it to be commercially viable. But the really cool thing about it, if you pardon the pun, is that these are hollow aluminum extrusions. And Alan had the foresight way back, before I was even involved, I think, to think about where that we could possibly pass water through these to cool them, to cool the wind tunnel, to keep it from cooling. So that the heat that we see in the wind tunnel is primarily generated by the friction of the air. A lot of people think, oh, the motors get warm or whatever, and so you're blowing that air and it's pulling the heat off. But electric motors are very efficient. They're like 97% efficient, somewhere 95, 97% efficient. So there's very little heat that actually is generated directly from the motor itself. The bulk, far and away, way more than the ambient temperature. Like you have, your air conditioner at home is primarily trying to cool your home because of the heat from outside, the sun, radiant heat, or the warm temperatures outside. On a wind tunnel, far and away, way above any of that would be a second order effect in a wind tunnel, the ambient heating. It's all friction heating.
It's the air just rubbing against each other.
Right, rubbing against each other.
Itself.
Right, itself, and so that's, and against the walls and that sort of thing. And so, we work on smooth flow paths and things like that, nice, efficient turns. But on the cooling side of this, getting back to your original question, is at one of the turns, we number them 1 at the top above the flight chamber, 2 in the corners, 3 at the bottom, and 4 is right below the flight chamber. In turn 3, in most of our tunnels, the cooled tunnels, some of them we cool more than one turn, turns 3 and 4, we pass chilled water through these turning vanes. And they're hollow aluminum extrusions and fairly thin wall. And the concept of cooling a wind tunnel this way is not something original to us, but to apply it in our application the way we do is original. We actually have some patent, or a patent, on that technology.
Cool.
And exactly. See, it's catching on. So anyway, it really is, and I love puns. So I always have fun with that. So there are a lot of puns in the wind tunnel.
I have some questions about the inlet contractor, because I know that that's really important to how the tunnel performs. But can you kind of talk us through that and the science of how that works?
Yeah, I touched a little bit earlier on on what we were doing when I was comparing the single pass, or what we call an open tunnel, to the recirculating tunnels. And that is that we try to put the fans as far in front of the test section, the flight chamber, as we can, because we can make the flow quality of the air better before it gets to the flight chamber. Okay, so that's what we do. That's just a piece of what we do, but the inlet contractor plays a really important role in that. If we have, in a perfect world, what we try to do is we try to achieve about a 6-to-1 contraction of the air. And what that does, that basically, in airspeed terms, what that means is we accelerate the air 6 times. So if it's going 25 miles per hour at the bottom of the inlet contractor, when it reaches the flight chamber, it's going 150 miles per hour.
Okay.
So 6 times that.
Just
over that
smaller.
Short distance, just from getting smaller. So and what happens when you squish the air down, that's my technical term for it.
Yeah.
So when we contract the air or squish it down, we're basically squishing all those molecules of air together much tighter. And what happens is, and they're accelerating, and that gets rid of a lot of the turbulence.
Oh, okay.
So the real magic in it is how you design that inlet contractor. And we work with, like I mentioned, I get I have the great fortune of leading a lot of the team, but there are a lot of smart people out there that are really responsible for this stuff, and we've got a couple of retired NASA aerodynamicists that we work with. One of them in particular that we spend most of our time with, and he's done a lot of his whole career was with NASA wind tunnels, like the 40 by 80, 40 foot by 80 foot test section tunnel.
That's so cool.
And yeah, some of my favorite times personally are just sitting down having a discussion like you and I are having now with him, and just listening to him. He's fairly up in age nowadays, but he really enjoys this, and he's really sharp, and we have learned a lot from him. But he is the one that helps us design these flow paths. When we do a tunnel design, we start with the flow path. We don't do anything else. We don't worry about anything else. We go, how can we make the flow path be most efficient and fit the other constraints that we have, the size of the flight chamber. It's all kind of driven by the size of the flight chamber.
Okay.
And then what we try to do is, for efficiency purposes, and the inlet contractor, a piece of that is we try to slow that air down as fast as we can after it gets out of the flight chamber.
Okay.
For a couple of reasons. One is the slower the air is, the less the drag,
Okay.
the less heat generated. So we not only takes less energy to push it around, but it also takes less energy to pull the heat back out, because we're putting it in and taking it out in these actively cooled systems.
So you're trying to...
So you're kind of paying for it twice, sort of.
Right.
But the efficiency of the cooled tunnels, because we don't have any louvers in there, we have a whole lot less drag. And so they're effectively, we're still working on refining some of the numbers, but they're effectively about the same efficiency.
Okay.
Maybe the cooled tunnels, the actively cooled, may be a hair more efficient even than the louvered tunnels, even though we have this whole chiller system and everything that we have to power and pull all that air out. So, so the inlet contractor is really the magic of keeping of getting rid of any turbulence that does exist as we go around this loop from everything that we do prior to the inlet contractor.
And then to slow it down, does it just open back up at the
We
top?
just diffuse it as quickly as we can. And when I say as quickly as we can, what we're up against is if you diffuse at too great of an angle, you'll get flow separation
Oh, okay.
off of the walls. And that's speed dependent, shape dependent, I guess somewhat density dependent as well, but we don't, that's a minor factor. But
And flow separation is turbulence.
it creates turbulence, because what happens is the air is running up along the surface, and then it would separate, and you have like this dead zone, and then it reattaches at some place along the loop, and so you've got this sort of buffeting going on in your airflow, and that's really kind of basically what turbulence is.
Okay. We don't always talk about Bernoulli, because sometimes we're working with younger students, but for like advanced high school groups or college groups, we do talk about Bernoulli's principle, and that when you speed up the air like that, the pressure goes down. So I've been in older tunnels where they have to close all the doors when the tunnel's on, but then in Austin, we can leave the doors open to the wind chamber, right? So
that's right.
There's something going on with the pressure. Can you talk about that?
That is another really, really cool feature. And I personally until we had the tunnel here in Austin, because I've lived in Austin throughout my experience with SkyVenture and iFLY. I always heard and thought that would be a big deal if we could somehow do that and allow the doors to be open, but I didn't really realize it until I saw the operation here, and we had a tunnel here in Austin where I could watch the operation on a regular basis. And it's big, it's huge. And what we do is, with Bernoulli's principle, basically the faster the air flows, the lower the pressure is relative to other places in the loop. So as the air goes up, the highest speed air in the whole wind tunnel is in the flight chamber.
Right.
Okay, we're basically flying in the Venturi. Okay. And then we slow it down as quickly as we can, all the way around the loop. Slow it down, slow it down, slow it down, slow it down. There are a few constant cross-section places where it's just constant speed. That's primarily underground. And then we accelerate it just in the last few feet. Like for instance, here in Austin, it's just 17 feet. We slow it down for, I don't know, a couple hundred feet probably.
Okay.
And then over the last 17 feet, we accelerate that. So the slower the air gets as you go around the loop, the higher the pressure is getting, okay, because it's going slower and slower and slower. But that's higher relative to what? So it all depends on where you vent the tunnel to ambient.
Okay.
So let's talk about the louvered designs or the open tunnel. They're really the same, one and the same, relative to Bernoulli. Is that in a louvered tunnel, the recirculating louvers, so you got the louvers over here in the return air tower, they're open to ambient. In the return air tower, you're almost the slowest air that you have in the whole tunnel. It's slightly faster than the slowest. And so what happens is that becomes your reference to ambient.
Okay.
So this is slow air, and then back over here in the flight chamber, you're going fast. So fast is higher pressure, right, than, I'm sorry.
Fast is lower.
Fast is lower. I'm getting mixed up myself. Fast is lower pressure. So, so what happens is in the louvered tunnels, the flight chamber is way below ambient pressure, to the tune of about 90 psf, 90 pounds per square foot.
Okay.
That's a lot of pressure. And so in those tunnels, whenever you're flying, and it depends on the airspeed that you're flying at, that's at the highest airspeed. So whenever you're flying like a first-time flyer, it might be at 45 psf or something like that. But you can't open these doors, or you could, but it takes a lot of load to open up the doors to be able to exit the staging area, the room that's on the edge of the flight chamber. Those doors, in order to have an actuator large enough to open the doors against that kind of pressure, becomes a safety issue. We could build something that could pop that open, and it would, and you'd suck a bunch of air in, from the building, which also wouldn't be good. And you'd be slamming doors in your building, and so it becomes a safety issue.
Right.
Because if you pop that open, doors, the front door of the building would slam shut if somebody's, because it's sucking so much air. And also the actuator that it would take to push that open, when you go to close it,
you could cut your arm off.
Yeah, you could break somebody's arm. And that's an honest. And some of the tunnels that we have that are louvered tunnels, and as well as the open tunnels, the single pass, we have an actuator, but we set it as low as we possibly can to where you wouldn't want to, get anything, so you don't hurt anybody.
Right.
So you can't really, so it's not practical to open those. So what you have to do in those situations is, if somebody, say you get in there and a small kid gets scared, or say somebody has to go to the restroom, or like with skydivers, they like to go in and out. They don't want to just be captive in the staging area. So what you have to do is you have to stop the tunnel down, run the tunnel down to 0 so it goes back to ambient. Slowly open that door, open 7 or 8 seconds, just really slow, because screw type actuator. And then somebody goes out and you have to reverse the process and spin the tunnel back up, and the whole process probably takes about a minute, and we sell time.
Right.
Okay, and when we're busy, I mean, if you add that up, I once ran the calculation, if you added up a minute, say if somebody went in and out each session, or whatever, it's big numbers in revenue.
Right.
So what
and
we
energy too from
and energy too.
winding
Well,
down
energy too.
that.
Yeah, and that's another good point.
So when you're in a tunnel like that and you're flying, do you feel like a pressure like you would on a plane?
Feel a little bit. You feel a little
in
bit,
your
kind of like on
ears?
a plane. You can
Okay.
feel a little bit, but not
that.
so much. Yeah, it's not much, not enough to be a problem for anybody. So what we did, the big breakthrough then was what do we do to be able to open these doors during any run, like we do here in Austin. Austin was the first one that we built with that style, and basically all we do is, because the relative pressure because of Bernoulli around the loop stays the same. You're going to have low pressure in relative to the rest of the loop in the flight chamber, higher pressure elsewhere. Well, the slower speed air is that instead of venting at the louver, whenever we decided to go with the actively cooled system, that said, hey, we don't need these louvers anymore.
Right.
So we still need to vent this tunnel. We don't need to, but we want to vent this tunnel someplace. So we actually vent it through the staging area, which is part of the flight chamber,
Okay.
the little room on the side. And we vent it down through the floor in most cases. Some of them we vent it up and then out the back wall of the building.
Okay.
And so it's, to the average person, they don't
even
see
know that.
this, don't even know that.
Yeah.
Just assume, hey, I can walk in and out of this thing. So what happens then in that case is that keeps the flight chamber and staging area at ambient pressure.
Okay.
And then instead of, the rest of the loop that's slower, it's at higher pressure. So this all now is, goes up to, in the highest pressure location is as high as about 90 to 95 PSF in some places. So that creates other issues, because now we have to seal that.
Okay.
Every joint we have, and it's a much larger volume. Before we had low pressure below ambient in the flight chamber. It's a much smaller volume compared to the rest of the tunnel. And so we worked real hard on sealing this part. Now we have to seal all the rest of the structure, and it's double.
It'll just.
Because anywhere you have a
out.
joint, and so, because that's higher pressure, whatever you blow out there is going to be pulled in through the vent.
Okay.
Externally. So if it's 100 degrees outside, and you pull 100 degrees F or whatever, and you're anywhere where you leak, you're pulling hot air in across the patrons, across the customers, and so we precondition that air.
Okay.
So that comes at a bit of a cost as well. So we have a system to do that, and then we, in whatever we don't cool there, we cool with the primary system. So it costs us in cooling costs. And we have to size our systems bigger to be able to handle that.
Okay.
So that's what that presented. So anyway, so the kind of summary, the whole Bernoulli thing, if we vent wherever we want to keep ambient, whatever location of the tunnel we want to keep ambient, that's where we vent. And so that makes it capable to go in and out the doors
Very cool.
at any place. And then it also allowed us to design a door that took much lower load to open, so we didn't have the safety issue.
Right.
So, one of the tests I personally run whenever I get a chance to set up one of the doors is I stand between those doors and just let them close on me.
Wow.
And it's, everybody goes, whoa, why'd you do that? But because they're used to the old doors. But yeah, it's, so that's how we got there.
Yeah, no, that's great, because we talk about with the students the engineering design process, that when you solve a problem, you know all of these other little things come up that you have to think about, and then you're constantly solving new problems. So that's wonderful. When new flyers come in, the first thing that's on their mind if they're nervous is safety, and like, is this safe for me, right?
Right.
So you talked about that, but can you talk about some of the other safety features?
Sure.
Like, we have to start with the net, because that's like number one on people's minds is like, am I going to fall through the net?
Right. Yeah, it's pretty, it's sort of a funny story about that. Whenever we have the opportunity to go out in the field during a construction, during the build process of the wind tunnel, some of our construction people that work directly for iFLY that are on site, they'll be out there and they'll have some contractors out there, and they'll be standing on, our guys will be standing on the cable floor net. And they'll ask those guys, the guys will come over and they'll look and they'll go, I don't know, they want to look down, and he'll go, come on out here. And some of those guys, some people do it, most people, a lot of them will go, no, I'm not going out there. So the truth is that one of those cables would support you.
Okay.
And
So
you've
yeah,
got
what's the load
hundreds of them. Yeah, they're stainless steel cables. They're like 3/32 diameter and of an inch, and which is about what's that, 090, and they are, it's very, very safe. Each one is spring loaded. We have springs on each ends of the cables, and so it's kind of like a trampoline when you walk in there.
Yeah.
And part of the safety part of that design is that there's the cables are woven together, and what happens is there's a lot of friction between those cables, and so as you walk on it, or say if you fell and you needed really to count on that net to help keep you up from falling below, is it dissipates a lot of energy within the net itself before it ever hits a stop, like a hard stop, and that's by design.
So it absorbs
the
energy.
That the friction everywhere where those cables cross one another, there's a lot of friction, and that's why they wear over time, and we have to change them out periodically.
Okay.
And that happens, one and two, one here, two there, that sort of thing, over time. But that friction dissipates the energy that you're putting into the net, and then as a last ditch, all the springs, reach their limit. They're fully compressed, and then it'll stop. And it's extremely safe.
Lots of safety factors.
Lots of safety there. Some of the other things, the big piece that is the primary safety feature is not a machine design thing. The primary safety feature is the instructor. The instructors are highly trained, very capable individuals. They go through, the course that they go through to become an instructor is so rigorous that there are a number of people that don't make it.
Okay.
I don't know what the ratio is, but not everybody that wants to be an instructor can be an instructor because they're just not physically capable. And these guys are trained, guys and gals are trained to keep you safe first, and then secondarily they teach you how to fly. So their primary job is safety, is keep you safe, and then they put on a pretty good show too.
Yeah, they do.
But that's one thing we do. We have like a rubber bumper around the door.
Right.
The whole conversation we had about airflow quality, that's all about safety.
That is.
One is, from a high-end flyer, they want good quality airflow so they can do what they want to do. So talking about skydivers and, people who compete. But for the first-time flyer, if you have good, solid, flow that's not turbulent, good even flow. So, we talked about like the prop type tunnels before being turbulent. Well, they also not only are they turbulent, but the airflow, the airspeed basically across from wall to wall is not even. And so you like fall off of it. You fall off the edge of it, that sort of thing. So there's like a high speed zone in the middle. In our tunnels, they're very even wall to wall. So whenever you fly here or fly in the center or on the other side, you really can't tell any difference.
And is that all from just the design of like the plenum and everything?
That's the design of all of that stuff together.
Okay.
Yeah, like I said, the inlet contractor plays a big role in that. But what all the stuff that we do, the rest of the loop, and putting the fans way early, all that stuff
awesome.
plays into that. Yeah.
Okay. How about the glass? The glass is huge.
It is.
Special shape. I've heard like mythical stories about the glass. when we first started doing the program, we wanted to write on the glass with a dry erase marker and do like calculations, and they were like, "You cannot touch the glass." Like they did not want that.
If we broke a panel, it would be a really bad day.
Yeah.
It would shut us down for a long time. But I didn't probably tell you this, but yeah, you could probably do that. That probably wouldn't hurt it.
Oh, okay.
Yeah, we used to use acrylic for our windows, and the problem with acrylic, even though it's beautiful when it's nice and clean and everything, it's very hard to upkeep. You can't use like Windex or anything like that. You basically use maybe some citrus-based cleaner. That's about the strongest thing you can do, and there's a lot of upkeep for that. And instructors clean every night. You can ask instructors who work in those tunnels versus the ones who work in the glass flight chambers. The glass ones are much easier upkeep. Problem is that they're harder.
The glass is harder?
It's a little harder if you fly into it. It's less flexible, stiffer, I guess I should say.
Okay.
Stiffer than the acrylic. If you were to slam into the wall or whatever when you're flying, the acrylic gives a little bit more so that's a positive for acrylic. But glass is where we're going and where we've been, for the last several years.
Uh-huh.
For instance, in the Austin tunnel here, it's 4-meter tall glass. We have some as large as 8 meters that we did. We did a tunnel in Dubai, and we've done a couple more since then that are like that. In the Austin tunnel, in the 14-foot tunnel, they're 2 layers, 10-millimeter glass. It's laminated, so it's bent, tempered, laminated. So if you were to break it, first of all, it'd be very, very hard to break.
Okay.
But if you were to break it, it would shatter, but it would stay together. And one layer would probably break, the other layer would probably not break. And it would just be a bunch of little tiny pieces, but they wouldn't come loose. That's, a design constraint, because we didn't want, like, if something strange happened and it broke on the inside, we didn't want all these pieces of glass like floating around the tunnel. So it's laminated.
Okay.
So we don't have any single ply glass. It's all at least 2 layers laminated together. So if you do break one, the little pieces stay as part of the window. So that's a safety issue, like we just talked about.
Somebody told me there's only like 2 or 3 places in the world that will make glass like this, because it also has to be really, the clarity is so good. You want to be able to see. Right,
exactly. Right. And I wanted to say one. I was
trying to remember.
There was one more thing from a safety standpoint that's kind of comical that I wanted to mention, and we'll talk about that too. Is our design? When we were designing, we're like, well, how strong do we need to make this? Okay, we can. Yes, there's the pressure load, and we design, even though we have an ambient pressure flight chamber, say in the newer tunnels, in the cooled tunnels, actively cooled tunnels, where we're venting from the flight chamber. We could have an abnormal case where we had something, we have to have like a series of like 3 different things that happen. You have to be at like maximum airspeed, and you have to have your vent to ambient, your vent that you want to have at ambient has to be fully closed, and you have to have a breach someplace else in the slow part of the tunnel that does vent to ambient. So if you had all 3 of those things happen, which is highly, highly, highly unlikely, but if all those happen, then you could get a flight chamber that's at minus 90 PSF, so that worst case. And so even though we're normally at ambient and at 0 pressure there, we still design it as if for that worst case.
Okay.
So that's why it's so thick. You look at it, it's like, well, it's ambient. Why do you make it so thick and multiple layers and all that? For safety.
Yeah, no, that's
This is related to the whole safety thing.
Right.
And so we don't want, even in that absolute worst case, we don't want any problem. So, and your other question?
Was about the people who make the glass. I heard there's only a couple places to get it. Yeah,
there's one in China and one in Germany. And then there's also a place in Mexico who we haven't done business with yet that also does it. But there are very few places that can make glass this large. In fact, we're in the U.S. we can't get bent, tempered, laminated glass this large, which really surprised me at the beginning of all this, that we don't have that capability in this country. The machines that are, even though there are multiple companies that can make it large, there's only one company that makes the machine that makes the large glass, and that's the company in China. So they both make the machine and make the glass. So a lot of our glass is made in China, some of it's made in Germany. And
who are their other customers for glass?
Their primary customer is Apple.
Oh.
You go to these Apple stores, they have these huge glasses. In fact, Apple is, to our knowledge, they're the only ones that make bigger, or that use bigger bent, tempered, laminated glass than we do.
For their stores?
For their stores.
Oh, wow.
Yeah, they have these gigantic glass. I don't know, if you've not been in an Apple store, you should go to one next time, because they have some fantastic stuff. So we're really...
I'm going to just run into the window. You're like, because I can. Mark told me I can.
Yeah, so we're piggybacking on really a lot of their effort to, as far as technology goes, to be able to build large glass.
Oh, that's so interesting. So. Really cool. Well, how about any other safety things we didn't talk about?
Well, a lot of it's process. We do, again, based on the instructors and how they handle it. It's part of it's from the training that we do, the training session that each flyer has to go through before they are allowed to fly. So, they receive training, which is driven by taught by the instructor for their session.
Okay.
That's a lot of it. Other safety things, well, yeah, there are some from the machine standpoint, like if we were to lose power or, have that sort of thing happen, we have a control shutdown. Now, we can't control shutdown if we lose power to the building, but if we have like an emergency stop, like somebody hits an e-stop, somewhere, like there's one above the flight chamber doorway. Say gets in trouble in the flight chamber or gets hurt or something, and they want to slow it down, and for whatever reason the person at the control station, this would be really, it's a very unusual sort of thing, but if there's an emergency stop, an e-stop on the control station, and there's one by the flight chamber doorway, and so either the instructors can hit that, and it doesn't just like shut the tunnel down immediately, it'll spin it down at a controlled rate, so that if somebody were high in the tunnel, they don't come down too quickly. And then the other thing is our fans are designed with we have aluminum blades in the fans, and it's fairly massive, and so there's a lot of inertia in the fans. And so with the 4 fans, it takes a while for those to spin down. And we've done testing. When we're here late at night after the business is closed is when we do most of our testing here. As an engineering team, we've flown. Alan Metney, the CEO of the company, did some of the testing with us. He got up and flew up high into the primary diffuser, and we shut the power and to see how far it went progressively higher and higher and come down and see. And there's sufficient inertia in the system to allow you to stay safe in those situations.
You mentioning the fans reminds me that one of our educators had a really specific question about the fans and how fast they are. What's the max RPM? And asking about the fan tips and if they're subsonic.
Okay.
Even when they're
when we run at maximum airspeed, we set up the pitch of the blades to give us maximum airspeed whenever we run the fans at about 900 RPM. So it's based on what would be a 6-pole motor speed. Actually an 8-pole motor speed, I'm sorry. But we're only running at 45 hertz. The fan motors are driven by VFDs, a variable frequency drive. So we have, if we in a 4-fan tunnel, so we have dual loop and single loop tunnels. So we have air comes up, it splits, goes around, comes back together. That would be a dual loop. We have 2 fans on each side, so that's a 4-fan tunnel. We also have some tunnels that are single loop, where the air goes up, comes back around, and we have 2 fans on one side. We have a variant or 2 from that, but those are the primary designs. And in those, and I'm sorry, I'm forgetting your question.
Oh, about the tips.
If
they're subsonic.
So what we do is we set the pitch of the blade such that we get our max airspeed when we're running at 45 hertz, which is what we drive the motors, the frequency goes in, and that turns at about 900 RPM, maybe just slightly less than that. At maximum airspeed, which is about 160 miles per hour. We can run it faster. We can change, pitch our blades, and we have enough horsepower to drive it faster, but that's the fastest we really need to go. And whenever we're at that maximum speed of the fan, the tips are definitely subsonic. We wouldn't want them to be sonic; it'd be very noisy, and we'd have other issues to deal with. Though it's about, I ran a calculation, it's about 0.4 Mach, I guess. So it's a little, about half the speed of sound. At the tips.
An activity we do with our high school students is that we have them measure their bodies, and they predict what their velocity is going to be in the chamber. And so then we're using the velocity readout to record what their speed is. But the instructors, I know, they all talk to each other in terms of percent power. And they say, I don't look at the velocity reading, but that's what we use anyway.
That's what you should look at.
Is the percent power?
Well, no. No, it's your velocity, because that's what you're,
All right, so can you talk about that? They're measured different. They must be measured differently.
Yeah, it's really, it used to frustrate me as an engineer, but I've gotten used to it. I talk in their terminology now. Basically, the percent is just percent of maximum airspeed. Percent, not really even airspeed, but percent, I guess, depending on the drag, it's percent of throttle setting from 0 to 100%. And if you go from one tunnel of one design to another tunnel of a different design, talking about, say, a 14-foot tunnel to a 12-foot tunnel or a 16-foot tunnel, those percentages are going to give you a different airspeed. Slightly. It won't be, so 80% here in Austin in a 14-foot tunnel. If you go to you know, a 12-foot tunnel in Colorado at Denver, 80% and 80% are not necessarily the same airspeed.
Okay.
So from a teaching perspective, you really need to be talking about airspeed.
Okay.
That percent is just, and it's an easy way, and plus they communicate with hand signals,
Oh,
you know,
right.
and it's a lot easier to go from 0 to 100 than it is in, you know, 143, you know, 125 miles per hour, whatever,
Right.
you know,
With your hands.
with your hands and stuff. So it's just,
Gotcha.
yeah, and so, you know, most of the guys fly at the same tunnel all the time, so it really doesn't matter. They get used to that. And they ask me what speed, I'll tell them, you know, 88% or whatever. Same thing. I don't. You ask me what speed you fly at, I go, you know, I'd have to look.
Yeah.
So after a while, you get used to that. But airspeed is airspeed. It's the only thing that's constant between, you know, from one tunnel to the next.
And that's measured with those pitot tubes.
With the
that are
pitot
hanging
tubes,
down in there.
right. And we put those just below the net.
Okay.
And so they're in good quality airflow. It's not, you know, above the flyer. We'd have some turbulence that's created by the flyers themselves. And so it's in one of the best quality, and plus airflow locations, plus it has to be where it's measuring max airspeed, so it has to be right up near the flight chamber.
And then we had a question about, is that absolute versus relative airspeed? So this is coming from a pilot who...
Yeah, that would be, I'm not sure what he's thinking. You know, there might be something here I'm not taking into consideration, but I would call that absolute. You know, now we do not correct for pressure, you know, for ambient pressure. So as we get higher, which would be altitude driven. Now we do have the ability to, in our control system, to set it for the given altitude that the tunnel is at, so it will correct for, say, the average pressure at a given location. So if you're in, you know, in Denver, you're at 5,000 feet, you know, or so, and versus Austin, where you're at, you know, 600 feet elevation, the density of the air is a little bit different. So we do correct for that for a given location, but it's not active like as it changes throughout the day.
Okay.
So same thing for humidity. We don't correct for that.
Gotcha.
So airspeed, you know, is affected by that. It's affected also by temperature. So in the cooled tunnels where we keep the temperature in a pretty small range, that factor doesn't come into play much. In the open tunnels or the louvered tunnels where the temperature does vary or can vary significantly, you know, we don't correct for that. So, you know, it's good enough for what we're doing.
Pretty close.
Yeah.
Okay. I definitely want to ask you about what's coming next for iFLY. What's exciting?
We've got some really cool stuff going on. There's some stuff that we touched on before the interview that we have a 32-foot tunnel that we've already designed it. There's still, you know, it's in fabrication right now, and so that's a 32-foot diameter flight chamber. And had the opportunity last week, as a matter of fact, to go out to Florida to one of our fabricators to look at the inlet contractor. We mocked it up, the bulk of it. And for instance, the inlet contractor on the 14-foot tunnel here in Austin is about 30 feet or so, approximately, at the bottom, and 14 feet at the top, of course. This 32-foot tunnel has a 68-foot wide piece at the bottom, or is the length of the size of the inlet contractor. It's 38 feet tall as opposed to 17 for the one, say, here in Austin. It's made up of 80 separate pieces of fiberglass and some other structure, and it is gigantic.
Yeah. And that's going to go where?
That's going to go in Abu Dhabi. Yeah, at Ferrari World in Abu Dhabi.
Of course.
So yes, of course, right. So yeah, it's really fun. You know, we're, like I say, in the fabrication stage of that, and that's supposed to ship at the end of the year over there and be constructed sometime next year.
So what, I mean, in going wider and wider, what are you running into design constraint-wise?
Well, one thing we didn't talk about earlier when we were talking about the venting system is that whenever you, and this is related to Bernoulli, again, is that when you're sitting at, you know, with the tunnels not running, you have the same pressure throughout the whole loop. Whenever you spool the tunnel up, you know, run it up the higher airspeeds, higher and higher airspeeds, because of Bernoulli, the slower air is at a higher pressure. So to achieve higher pressure, you have to pull air into the tunnel somewhere.
Right.
You know, to make up for that. And so that all comes through your vent. Okay, in a small tunnel like, relatively small,
Yeah.
like we have here in Austin,
This used to be the
this
big
used to be
tunnel.
big. Yeah, it used to be big. The volume of air that it sucks in through that vent is manageable going through the doorway. You have, flight chamber doorway where you go from the staging area into the flight chamber, and that's where all that air has to enter the tunnel, and then whenever you slow the tunnel down, it blows back out of there.
Okay.
This act was actually a phenomenon early in our design phases that we didn't necessarily predict properly. And we had to do some learning. This was some of our growth that we did as engineers and aerodynamicists. When we look back at it, we go, of course, but it was something we didn't predict properly the first time. And so we paid a lot of, very close attention to that. And so if you imagine a 32-foot tunnel, the volume of air in this thing is huge. And so if we're having to do some other special things for venting so that we don't blow all that air through that doorway, that we would be like blowing people in and out. It would be a very, very high speed, like hundreds of miles per hour.
Oh, wow.
Through that, as opposed to maybe 30 miles per hour through that doorway. So we're having to do things to allow for that.
Oh, cool.
And so it's presenting a challenge. So we won't really know. We're going to do everything we can from an engineering perspective to account for that. But whenever we first run the tunnel up, I mean, it's a prototype. We sell our prototypes, right? We design a tunnel, and we don't have the luxury of building one and testing it and then selling it to somebody.
Right.
So we're going to be over there and having to run through a very rigorous test regimen to make sure that this thing operates the way we expect it to operate. So noise is, that was one of the things I failed to mention earlier when we were talking about what are some of the advantages of the closed loop tunnels,
right.
The recirculators. An open loop tunnel, I was just in Orlando last week, and I drove by the old one, and from the street you can hear the thing run. Whenever it's running, even when it's not running at max, you can hear the thing. In a recirculator with the louvers, you can still hear some because there's a big door for it to enter, but in our closed loop tunnels, in our actively cooled tunnels, you can be out from the building, you don't even know things running.
Right.
You can be in the building sometimes, some places, when it's running at low speed, not necessarily know that it's running.
Right.
So we've put a lot of resources, a lot of effort into, there's a whole part of our internal team that's been working the whole noise aspect of wind tunnel stuff, from aerodynamics in the fans. We have some resonant frequencies that are, when you run the fan by itself in just open air, when you test it, it doesn't create that noise, but it does whenever we're in the wind tunnel, and we've been chasing some of those issues. I say chasing, we've been successful in some areas, other areas not as much, but that's some of the ongoing R&D. You wonder, well, what are you doing? What more can you do? We've done a lot of different tunnels, but that's all part of, we're doing a lot of refinement, a lot of detail work, trying to take cost out. What our goal is to get the cost low enough to build one of these things so that it makes, ultimately, perhaps we could even reduce ticket prices and take it to smaller markets rather than just being in larger cities.
Right.
And so that's one of our goals. And if you can do that, then of course the market opens, and you got more people that can fly and more demand, and it makes better, more success for the company as well.
Right. And I was going to ask you about just a little bit more about energy efficiency. Some of the kids who come through are asking like, wow, your electric bill must
It's got to
be
be
so
big.
high.
It is huge. You wouldn't believe. Yeah, with it's tens of thousands of dollars per month.
Wow.
I don't know if I can say exactly what it is, but yeah, it's
Probably varies.
Yeah, it varies. It
different
varies
ones.
depending on what's going on. But yeah, we're talking at this tunnel here that we're sitting in. I'm aware of what those numbers are, and yeah, it's multiple tens of thousands per month.
Right.
So it's
that's crazy.
a large number. Yeah.
Is iFLY thinking about doing anything with like solar or alternative?
It's our on this tunnel that we're sitting in. To run it at maximum airspeed is about a megawatt of energy, power to run it. It would take a lot of solar to produce that. I think the San Francisco tunnel, this is old data from years ago, but I think they were purchasing
solar power from their power distributor, from their power company, so that they were, quote, green, burning green energy. So, I mean, there are ways, probably more on a secondary, from a secondary standpoint to do that,
Right.
than directly, because it would be tough. There's not enough area here to really produce enough energy to, from a green energy standpoint,
Right. Okay.
to do that,
Very
to
cool.
power the thing.
Cool. Well, one on the moon next.
Yeah,
It's the
really.
only place that doesn't have one.
Really.
That's great.
So,
I think we covered so much.
you cover.
Yeah. Thank you so much, Mark.
bet. Yeah,
Yeah,
thank
this has
you.
been a wonderful interview.
It's my pleasure. I really enjoy sharing this, and I really enjoy sharing that with kids in particular.
Great. Good. Thank you, Mark, so much for all of this information. For you guys, if we didn't answer any of your questions, if you want to let me know, Mark has offered you could even call him in the middle of a field trip and he will answer your question in real time. But I'll pass your questions on to Mark. So thanks very much.